Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams. I am a former associate professor of electrical engineering with the University of Texas at Tyler, and I currently hold the rank of associate professor emeritus with that institution. Today, I want to talk about technology at the dawn of my professional career. And I call this Memories of DICKEY-john Corporation. And the years that you see there are the years of my employment with the company. You notice there is a gap. That was a time when I was on leave of absence to attend graduate school. But who or what was DICKEY-john? DICKEY-john, well, let me show you. Here's the company's logo from the early 1970s. You notice the logo shows corn, soybeans, and wheat. And the slogan was First in Agrionics, which sounds like a mashup of agriculture and electronics, and indeed it was. Farm electronics was their business. All of the equipment that they built for use on the farmstead was painted this color they called harvest gold, but out in the shop, it had a different designation. DICKEY-john was launched in 1966 by Robert Dickey and Jack Littlejohn, both of Central Illinois. The name of the company was a portmanteau of Dickey and Little John. That's why the John is in lowercase. I worked there for 10 years before the mystery behind the company name was suddenly revealed to me. And once the powers that be learned that I was privy to the secret at the heart of the company, they knew they had to get rid of me. But that's another story. Dickey and Littlejohn had a simple idea. They imagined a device that would tell farmers that their planters were functioning properly. Thus was the idea born for the planter monitor. And neither Dickey nor Littlejohn was an engineer, so they went to Sangamo Electric in Springfield to look for engineering help. And Sangamo engineers helped design them a planter monitor system that the seed sensor was a lightweight switch with a little flapper that a seed falling through the seed tube would strike the flapper, close the flapper, and the closure of the switch would flash a lamp to tell the farmer that a seed had just been planted. Seemed straightforward enough. However, the mechanical seed sensor proved to be unreliable in the farm environment. Sales were poor, and the infant company, after 2 years, was circling the drain of bankruptcy with its loans coming due, and it looked like it was all over. But then two events took place that saved the company. One was the personal intervention of Robert C. Lanphier III of the Sangamo Electric Lanphier family, and the other was the invention of a photoelectric seed sensor. So by 1972, the company was on a solid footing and built its own offices and shop in Auburn, Illinois, a town of about 3,500 people, located about 25 kilometers south of Springfield, the state capital. DICKEY-john profited greatly from the robust American agriculture market of the early 1970s, when farmers were being told it was up to them to feed the world, plant hedgerow to hedgerow, get big or get out, acquire more land and more equipment. Times were good, and DICKEY-john profited accordingly. It grew from about 250 employees in early 1974 to a peak of very close to 1,000 by 1980. Most of them were in Auburn, although there was a small contingent that worked out of a European sales and service center in the northern suburbs of Paris. The product line had expanded beyond the basic planter monitor by the time I joined the company in January of 1974. In fact, the very first product I worked on at DICKEY-john was a combine shaft monitor. It's a system that monitors the rotational speeds of shafts in the separator system of a grain combine. And if a shaft is running abnormally slow, it will alert the operator that something is wrong. Maybe there's a slipping belt, maybe a worn clutch, before something would go catastrophically wrong that would cause downtime. But another product they had was this handheld grain moisture tester. It was very popular, and one of the better known products of the company was designed for DICKEY-john by consulting engineer George Fathauer of Decatur, Illinois. And why design a handheld grain moisture tester for farm use? No. If you take your grain to an elevator and sell it, they're going to measure the grain moisture content, and there is an optimal value. And if your grain moisture content is either too dry or too wet, they'll dock you for it. So it behooves you to know what your grain moisture content is before you take your grain to sale. So let's take a look at some figures from this Fathauer patent. I think this was an interesting technology, very clever, and it performed quite well despite its apparent simplicity. This is figure 2 from the patent, and it shows the housing, which was a drawn aluminum can. Here you see a grain cell, which was actually a coaxial capacitor. And this was the first product I had ever seen that incorporated a liquid crystal display. Here's figure 3 of the patent, and it shows a spring, one of two. If you notice here now, going back to figure 2, here are two separate springs. The grain cell sits on top of this spring-loaded pedestal of sorts. And when you pour enough grain into the grain cell, the weight of the grain will overcome the tension of the springs, and the grain cell will drop slightly. And when it does so, it closes this power switch, which starts the measurement circuit. So then to turn the unit off, you just take the unit, turn it upside down, dump the grain out, and it turns itself off. Very simple to use. Figure 5 shows a cutaway of the grain cell, which shows it as a coaxial capacitor having an outer shell and an inner cylinder. And this plastic cone on top was meant that during the pouring process, grain would be pretty much uniformly distributed within the grain cell. And here's a diagram, figure 4 from the patent, viewed from the top. And we can see here the housing, the handle, the grain cell viewed from above. And here are the two springs. And one other thing to mention is this thermistor. A thermistor that was mounted in the side of the grain cell would measure the temperature of the grain, and it would allow a temperature correction to be made. Now, the operating principle of this was fairly simple. There were two radio frequency oscillators inside the unit. One oscillator was fixed. It was the reference oscillator, and the other one, part of its resonant circuit, was the grain cell. By dumping grain into the cell, you change its capacitance. It changes the operating frequency of the measurement oscillator, and a mixer circuit measured the difference frequency, and that was used. The difference frequency was used to produce a reading of grain moisture content. It was all it worked surprisingly well despite its simplicity, and it sold very well. It was a popular item with DICKEY-John's customers. But now let's go back to the core business of the company, the planter monitors. This was a patent issued to an inventor named Schenkenberg in 1970. It was originally assigned to DICKEY Corporation, but DICKEY-John purchased this patent. This was the first patent in which the photoelectric seed sensor was described. The drawing of figure 1 of the patent shows the tractor, the planter. Each of the 4 rows in this 4-row planter has a seed hopper and a planting unit. A planting unit digs a furrow in the ground, drops the seed. And this planting unit, each one was equipped with a photoelectric sensor in the seed tube. And each planting unit is followed by a compacting wheel that pushes the dirt back over the seed. There was a monitor console containing lamps on the hood of the tractor and a wiring harness that connected the sensors to the monitor console. Figure 2 and 3 of the patent show more details. Here is the seed sensor. There is the seed sensing chute. Figure 3 is an enlargement of the seed sensing chute, showing the light source on one side and the photoelectric sensors on the other. Figures 4 and 5 are transverse sections of the sensing chute from a 90-degree angle to the preceding section, which shows here the light source and the photoelectric sensors. The light source and the photosensors extend pretty much the full width of the outlet of the sensing chute so that the chances of a seed getting through that area without being seen were very limited, very small. This was the signal processing circuit that was described in the Schenkenberg patent. Here you see the photoelectric sensors, photoresistors, actually, and they, in connection with the resistor 62, formed a voltage divider. If the sensors, if something blocks the light to the photosensors or reduces the light falling in the photosensors, this voltage divider will cause the resistance of the sensors will rise under those circumstances, and the voltage at this point will fall towards the negative supply voltage. On the other hand, if the blockage is removed and illumination is restored, the resistance of the photosensors will decrease and the voltage will pull towards the positive supply rail. So the pulse that was the change in voltage appears here at this voltage divider is AC coupled to an emitter follower, which then drives a clipping amplifier. The output of that clipping amplifier was buffered through an emitter follower and applied to a lamp driver. So the idea was that momentarily breaking the light beam would produce a fixed width or constant duration pulse to the lamp, but also the system relied not on the absolute resistance of the photodetectors or the photosensors to determine that a seed had been dropped. It relied on a momentary variation in their resistance. That meant that the system was tolerant of dust buildup and ambient temperature variations that would affect the resistance of the photosensors. George Fathauer had a patent on a planter monitor himself. This was issued in 1973, which was very similar to the Schenkenberg and relied on photoelectric sensors. Here it shows a tractor, planter, seed hopper, planting unit with sensor, compacting wheel, the monitor console, and the wiring harness. One of the innovations that Fathauer made, though, was an audible alarm that would sound if one of the rows quit planting, which the Schenkenberg design did not envision. But Fathauer had a couple of different signal processing circuits in this patent. Figure 7 on the left is very similar to the Schenkenberg. Here is positive supply voltage and ground to this sensor. Item 36, element 36 here is the light source. 38 is the photoresistor. The photoresistor forms a resistive voltage divider with 60, AC coupling to a clipping amplifier and an output stage, which was connected to an external pull-up resistor in the monitor console. Fairly straightforward. Figure 8 was a much, maybe I shouldn't say much more sophisticated, but it worked on a different principle. This is what's known, well, in measurement systems, there are two kinds of sensing systems. There are deflection systems and there are null systems. A deflection system is like a bathroom scale. You step on it and the numbers change and it shows how much you pushed down on the platform of the scale. But there are also null measuring scales like those in doctors' offices where they balance the scale, you step on it, and then they move the weights until balance is restored. That is a null type instrument. This in figure 8 is a null type sensor. Here we have power supply and ground. We have a light source 36, and we have the photoresistor and a voltage divider. But we have here these Darlington connected transistors that draw the current through the light source. This forms a negative feedback loop. Let's say that something partially blocks the photoresistor. Its resistance rises. That causes greater base current to the Darlington connected transistors, which draws more collector current, which makes the light brighter. The light brightens to try to maintain a constant illumination following on the photoresistor. On the other hand, once the blockage clears, the resistance of the photoresistor drops It reduces the base current to the Darlington connected transistors, reduces the current to the lamp source to make the lamp source less bright. So you see variations. Whenever a seed passes, you'll see a pulse appear at the collector of the Darlington connected transistors. That pulse was AC coupled to a clipping amplifier output stage connected to the monitor. Let's take a look at some DICKEY-john planter monitors of the early 70s. This is a 4-row so-called seed flow monitor. And there are the row lamps, and there's the audible alarm that was envisioned in the Fathauer patent. Now, this is a much more complex device. This is a 12-row population monitor. It was also a Fathauer patent, a later patent, and it shows some resemblance to the seed flow monitor. Here are the row lamps and the audible alarm, but it has a display here, a population readout that read out population density, and I believe it was thousands of seeds per acre. The readout at that time was a 7-second segment incandescent display. LEDs were not bright enough in that era for daytime use, and LCDs were too expensive and too fragile. Here we have a knob that was called the population selector. It had a mark for corn, and on the top of the unit, it says, for other grains, see the operator's manual for the proper setting. Frankly, I really don't know what was behind that switch because I never worked on the population monitors. That you also had a row selector that allowed you to route the pulse outputs from any one of the selected rows to this mechanical seed counter. You count the seeds in any given row. In order to measure the area covered by the planter, you had to know its width, which was the row spacing multiplied by the number of rows. So there was accordingly a row spacing switch on the rear of the panel. And you had to have an external fifth wheel pickup to measure the distance covered, which of course is not shown in this photograph. Well, DICKEY-john was succeeding quite well through the 1970s in the planter monitors, and success attracts competition. By the late 1970s, planter monitor sales had reached about $12 million a year, and a company in Bloomington, Illinois, about 100 kilometers northeast of Springfield, decided to get a piece of that market. They hired a former DICKEY-john employee and reverse engineered a DICKEY-john planter monitor and produced their own design, which was sold under the name of Field Electronics. I'll get to that in a moment. Here's a photograph from the Bloomington Pantagraph newspaper of a Field Electronics planter monitor being tested in June 1978. And as you can see, they had much more advanced styling, and I've been told their electronic design was more advanced than DICKEY-john, but they copied the seed sensor. And that was a mistake. So DICKEY-john notified International Tapetronics of the apparent infringement of the Schenkenberg and Fathauer patents. International Tapetronics then formed a minimally capitalized subsidiary known as Field Electronics in response to the infringement suit, kind of put a firewall between the company and this potential infringement suit. DICKEY-john alleged willful and wanton infringement, entitling DICKEY-john to punitive damage. International Tapetronics conceded the infringement, but contested the validity of the Schenkenberg and Fathauer patents on the grounds of obviousness. They were, in their view, obvious extensions of prior art and therefore not patentable. At a bench trial in 1981, some of the claims of the Fathauer patents were found invalid, but the central claim of Schenkenberg and the design of the photoelectric seed sensor was upheld as valid, and the court also found that International Tapetronics had indeed willfully and wantonly infringed this patent. Both parties appealed. DICKEY-john to appeal the ruling against certain of the Fathauer claims, and International Tapetronics, of course, appealing against the ruling upholding the Schenkenberg patent and the finding of wanton and willful infringement. The Schenkenberg patent was upheld, as was the ruling of wanton and willful behavior on the part of International Tapetronics, And as I was told, the value of the judgment, actual plus punitive damages, exceeded the value of field electronics, and Dickey-John essentially put them out of business. Well, let's talk about some projects that I worked on myself during that time. As a matter of fact, here's my name listed among the inventors in this patent for this combine data center. Here are figures 1 and 2 from the patent showing a combine. The basic combine data center, composed of a CPU and a CRT monitor and had this machine parameters module, was to replace the gauges of the instrument panel with readouts on a cathode ray tube. However, the system was expandable. It had an open bus, and you could plug in other optional modules, such as, to monitor the separator, he had a shaft monitor module. I worked on one of these control modules. Mine in particular was a so-called load control module that used a torque sensor measuring the torque required of the separator mechanism and changing the ground speed of the combine to maintain a constant load on the separator. The whole system was field tested. It was found it worked. However, it never went into production because the company for which it was being designed, by the time field testing was wrapping up, the company was on the verge of bankruptcy, and they just simply canceled the project. Another project I worked on was a grain moisture tester. This was a laboratory quality instrument, but it had many similarities to the Fathauer tester. This was a diagram from the patent, which you'll see my name on. We have the measurement console, a grain cell, which was a coaxial capacitor, just like Fathauer. And here we had a holding cell with a thermistor and a dump mechanism. And in this case, the user would have to weigh out a certain amount of grain, like 250 grams of hard red winter wheat, and put it in this holding cell, and then initiate a measurement cycle. The unit would self-calibrate, and while it was doing that, it would also measure the temperature of the grain with the thermistor that was up in the holding cell, and then the flaps of this dump mechanism would drop, the grain would drop into the grain cell, and a measurement cycle would be undertaken. My contribution was the measurement circuits, which consisted of, like in Fathauer, 2 radio frequency oscillators. Here's a fixed frequency oscillator. Here's a variable frequency oscillator, which was connected to the grain cell, and a variable capacitor. Now, unlike the Fathauer instrument that was a displacement or a deflection instrument, this was a null instrument. This capacitor was driven by a stepper motor, and I will show you in a moment how we use that as a null instrument. In the meantime, there was a link circuit that connected the 2 oscillators through a Schottky barrier diode, and when the 2 oscillators were operating at the same frequency, you got a definite null or minimum value in the output voltage, the DC component of the link circuit output voltage. This design also used a device that I'd never used before and frankly have not used since, a dual gate MOSFET that was designed for radio frequency amplifier applications, while the second gate was used for automatic gain control. So how did it work? Well, this first graph shows capacitance versus rotation of that variable capacitor. It was an air variable capacitor. It had no stop. It could turn through a complete 360 degrees. And at the beginning, when the plates of the capacitor were fully meshed, you had maximum capacitance. You'd turn at 180 degrees to where the plates were their least meshed. And that's when you had minimum capacitance. And then as you rotated beyond that, the capacitance would increase again until you reached the original starting point. Now, during the time that the instrument was self-calibrating during the measurement cycle, while we were measuring the temperature of the grain in the holding cell, the stepper motor would run the capacitor through 1 revolution, and we would find the 2 nulls where the operating frequency of the variable frequency oscillator matched that of the reference. We would locate the locations of those two nulls, drop the grain, and then we would run through one rotation of the capacitor again and see how the null locations had moved. From that, we knew how much the capacitance had changed, and knowing the grain and its temperature and the change in capacitance, that became the data for computing the grain moisture content. Another one that I worked on was this, the Doppler radar velocity sensor. Now, I'm not showing the patent. I was not a designer. I was not an inventor. It was invented, it was largely the work of my good friend, Wesley Bachman. Wes did most of the design work of this radar sensor and its predecessor, by the way. I was given the job of taking this radar velocity sensor from prototype form into production. Anyway, the radar velocity sensor 2, as it was known, operated K-band, 24.125 megahertz. You might ask, why would a farm vehicle need a Doppler radar sensor? Now, it was a much better way of measuring ground speed than a fifth wheel on the ground, principally. It was the successor to the X-band radar 1, which operated 10.525 gigahertz. It used a gun diode microwave source and a Schottky barrier mixer as the Doppler transceiver. We did not manufacture this. We bought these from a vendor of microwave components. It used an aluminum circular horn antenna that was sealed inside this housing. And the antenna was mounted on a vibration damping suspension system to prevent vibration of the frame from the engine from being communicated to the antenna and being interpreted as relative motion of the antenna with respect to the ground, and so giving you a false speed reading. The vibration damping system itself earned its own patent, as I recall. It was mounted at 35 degrees below horizontal, and it gave an output frequency nominally of 132 hertz per meter per second. Now, we're going to talk briefly about the technology behind this, because this was actually this was interesting. The gun diode was a device that I had studied in a class in solid state physics in the second semester of my junior year. But here, for the first time, I was getting to actually work with them. The gun diode is a very interesting device in that it consists basically of a slab of N-type gallium arsenide, which has a very interesting and unique electrical property that as you start to apply an electric field to this slab that makes electrons move, the ratio of a change in electric field and the change in velocity produced by that electric field, here's the change in velocity on the y-axis, change in electric field on the x, that's known as the mobility. And the higher the mobility of a material, the better it conducts. So you start off with a relatively high mobility, but when you reach a critical electric field of around 3,000 volts per second, the mobility begins to decrease because electrons are transferred to another band of available conduction states that have much lower mobility. And so for a range of electric fields, the mobility actually appears negative. That is, the change in velocity with the change in electric field was negative. And if you operate the gun diode in that range, within that range, apply the right electric field to it, the right operating voltage to the gun diode to bias it in this range, it acts like a negative resistor. You pair a negative resistor with a resonant circuit and you have an oscillator. This is how we turned DC voltage into 24 gigahertz microwaves. Very slick. Well, I learned a lot about technology, about applying the theory that they pumped my head full of as an undergraduate to the real world. But another lesson that I learned at DICKEY-john was the importance of dealing with people. We had all sorts there. We had the full gamut of humanity. We had people whom you could trust with your lives. We had people whom you would never trust, never turn your back on. We had good, solid people who were technically competent, and we had some who were not quite so technically competent. And we had people who became good friends and I'm still in contact with, and others that haven't seen them in a while and don't particularly care. There were people that I met there. If I had if I had to walk through fire to work with them again, I would do it. And others, if I don't run across them again, I won't sit up nights worrying about it. We had our saints, we had our sinners, we had our empire builders, we had our self-important jerks, we had racists, we had sexists and misogynists, and we even had at least one known case of one of the company executives and his secretary who were actively violating their marriage vows. But enough of that. I'm going to tell you a few stories of human interactions from those days that I think are kind of funny. And I'm going to use pseudonyms. I'm not going to use actual names because I don't want to use actual names. So let me start off with one I call A Lesson in Italian. Now, there was a guy who I will call him Tony because that's the good archetypal Italian name, right? Who worked in technical publications. And he was from Italian background. He was very proud of his heritage. And I was down there dealing with him one day about service bulletin or user's guide, something, I don't remember what. And I wrapped up my business with him and I said, okay, Tony, catch you later. And I turned around, started to walk out, and he said, okay, mangia merda. Now, at that time, I didn't speak any Italian. I knew a few words, principally spaghetti, tortellini, mostaccioli, fettuccine, and ravioli. But that was pretty much the limit of it. But even though I didn't speak Italian, this was close enough to French that I did know that I recognized it. And I stopped in my tracks and I turned around and I said to him, why did you just tell me to? That's what he had said. Now, I'm guessing that he didn't say it maliciously, that this was probably something he said among friends, just as a gag, and it slipped out. But he certainly wouldn't have had any idea that I would have known what it meant. Anyway, I stood there with my mouth open in astonishment, and he turned bright red and looked down at his desk and would not look up at me. And after a few moments of letting him twist in the wind, I turned around and walked out. And I got out of earshot and I cracked up laughing. The poor fellow, he was so embarrassed. He wouldn't look at me for 3 weeks, I tell you. But anyway, misplaced digits. Dickey-John had a part numbering system for parts, electronic components, mechanical components, whatnot. Everything had a part number. And in cases like, let's say, resistors, where there's a basic form, but there are lots of different implementations of it, they gave them a 5-digit base number followed by a 4-digit extension. So 20177 was a quarter watt carbon film resistor, and the 4-digit extension would tell you specifically what value of resistor. 21563 extension was a film capacitor. 21526 was a small signal discrete transistor. 21562 was a tantalum capacitor. Now, these latter two that you see there were ones that, for some reason or other, today, 30 years after the fact, I got it with crystal clarity which was which. But back then, I had a mental block about which was the capacitor, which was the transistor. I don't know why, but I did. Well, I turned in a preliminary parts list to a fellow I'll call Larry, he was a retired Sangamo guy who'd come to work at Dickey-John. And his whole mission in life was to bring order out of the chaos of the universe by making excruciatingly detailed and accurate parts lists, which he called breakdowns. And to him, order and precision were everything. I one day gave him a preliminary parts list for a design I was working on to start working on his breakdown. And he ran across an error on my part. I had transposed the 6 and the 2 in the part number of a particular type of transistor. So the transistor part number didn't match the description. Okay, this is an error. But to Larry, this was not just an error. This was a moral affront to the order of the universe, and it called for divine retribution. He didn't call me on the phone, which he could have. Said, hey, we have a discrepancy here. He could have walked over and shown me the discrepancy, and we could take care of it. No, this guy walks over to my cubicle and takes a sheaf of papers, my parts list, and waves it in my face, literally, and says, what the hell are you trying to do? I'm just, whoa, what? And then when I see that, this transgression that's causing the thunderbolts of the gods to be loosed upon my head was just a transposition of 2 digits, an easy error to fix. After we straightened it out, he walked away feeling vindicated. I'm sure that he had saved the company from the incompetence and laziness of the engineers. And I had a hard time getting back to work the rest of the afternoon because I thought it was just an over-the-top reaction. But okay. And the third one that I want to talk about, it actually doesn't involve technology. It involves a bet on college football. Now, I worked with a fellow, and I'll call him Pat. He was a big fan of the University of Illinois Fighting Illini football. And one day he was in my office and we were talking about Illinois football, and happened to mention that in 1982, Illinois had played Michigan in Champaign, Illinois, and Illinois had lost by a score of 16-10, but Illinois had a chance to win it in the last seconds of the fourth quarter, but their drive was stopped. They were 4th and goal, and their drive was stopped by Michigan defense on maybe the 1-yard line, and they turned the ball over on downs and came close, but didn't quite pull it off. But the following year, for the first time in, I think, decades, Illinois actually beat Michigan. Now, notice where both of these games took place. They were both home games. Took place in Champaign, Illinois. And I happened to mention to Pat that Illinois almost beat Michigan at home in 82, but did in 83. And he said, no, they don't do that. They always alternate home game, away game, home game, away game. And I said, well, Pat, I don't know why, some kind of scheduling quirk, but they played at home against Michigan 2 years in a row. No, they never do that. And I said, but they did. And I knew it because I had listened to the 82 game on the radio and I'd watched the fourth quarter of the 83 game on television. I knew. But he says that doesn't happen. He says, you want to bet? And I said, okay, how much? $5. I should have bet more, as I knew I was right. Well, anyway, he says, all right, I'll go home over the weekend. This was a Friday. And I'll check my schedules and I'll come back on Monday to collect. Okay, fine. Well, by Monday, I've actually completely forgotten about this episode. I'm working in my office and Pat walks in. And he walks right up to my desk. He doesn't knock on the door, doesn't say anything, just walks right up to my desk. And he looks at me with like Superman X-ray vision, like he's boring a hole through me with his eyes. And it's kind of creepy. And I said, Pat, can I help you? And he doesn't say a word. But he pulls his wallet out of his back pocket, extracts a $5 bill, slams it on my desk, and says, you son of a bitch. Easy money. I should have bet him 50. Easiest money I ever made. Well, anyway. So, obviously, from the dates you saw, my career extended well past my years with Dickie-John. What was the end of the line there? Well, The boom times of the 1970s gave way to the ag bust of the 1980s, and many of the farmers who'd extended themselves financially to get more land and more equipment were caught holding the bag in the early 1980s, and it was a bloodbath on the farm. That meant falling sales for Dickie-John. It meant wage freezes, occasional layoffs, people getting discouraged and leaving on their own. And then the board of directors descended into chaos and open warfare over the direction of the company. There were rival factions vying for control of the company, and it seemed like to those of us who were working there, we felt like we were down in the bilges manning the pumps trying to keep the ship afloat, and they're having a fist fight up there on the bridge. Well, the truce that ended the fighting was an agreement to put the company up for sale. Robert Lanphier announced the sale on Christmas Eve of 1987, and he said that the new prospective owners had promised that it would be business as usual. Now, the sale didn't actually take place till the shareholders' meeting of 1988. But 4 days after the sale, the layoffs took place on a fairly large scale, including me. I was the only person in the design engineering group with a master's degree at that time. That kind of made me stand out as an expensive luxury. And so I was out. However, I had seen it coming. I had figured it probably was coming. And I'd been out looking for another job. And the day afterward, I got a job offer from a company in Wisconsin that made medical imaging systems. And that was the next chapter of my career. But, you know, having to suffer the consequences of events beyond your control, it comes with the territory of being an engineer. So to sum it up, I could turn to the words of that noted American man of letters and philosopher Kurt Vonnegut, who said, "So it goes." So anyway, I appreciate the time that you've spent today, and I hope to see you in future videos.